in one-dimensional structure using vibration tests. This is the content on this one. What I'm going to do very quickly are the objectives. We need a model for damage. I use fracture mechanics in a finite element program that I coded in MATLAB in order to make it faster. And I show a method and a flow diagram. There are two criteria that I came up with. One is the damage onset, how to find out the damage onset in this structure. And the second one is a simple one to see what is the half of the beam that has the damage. Because I used simplification method where you have a very similar uniform beam. So I use only half of it. I model only half of the beam. Then once I found where the location there are two possibilities, where the beam and where the crack would be, exactly. So there are two methods that I use, and I use a criteria. Then I'm going to show some test results that I did on the laboratory and experimental validation on a table that I'm going to show the statistics of the test. There were 4 cases, and finally the conclusions on this method. The background is that we can use this on industrial environment, simple ones, not too much details, but applications wise. I'm going to be using the splitting frequency method, where when you have a beam, you have 3 kinds of vibrations in general: the axial vibration, the flexural or torsional vibrations, and the flexing. This phenomenon happens on the flexing modes. The flexing modes, when you have damage, they split into 2 frequencies, 2 instead of 1. So I used that, and I confectionated some indexes, damage indexes. I put them into some expressions, and they are useful for structural health monitorings, and they keep track of the damage in an efficient manner, complies with minimum invasiveness. The method is robust, versatile, adaptable to many variety of one-dimensional structures. And the vibrational techniques take advantage of many tools coming from frequency spectrum sensors, transducers, computing, electronics. The validation procedures are for an international standard, and that could be used also on very high cycle fatigue standards. This is a general sketch where you can have the crack in one direction or the other one. And here you can see them in a circular cross-section. And this is an experimental result where you concentrate on one bending frequency, on one bending mode, and I draw 5 deep depths of the crack and how they are falling apart. They all reduce the frequency value, they all reduce, but the distance between them increases. So when I use this early structural damage detection is important, because if you don't have any damage, then the surface is 0. There's nothing in there. And you can use the expression in order to see if you have 0 or not. There are 6 expressions. So you can use them up in a statistical manner to get more information, to beef up the results. Here is the finite element that I use, 6 degrees of freedom. And this is the cross-section damage. I am assuming a straight crack. in anywhere in the finite element. And in this case, it's a circular cross-section Timoshenko beam. And these are the six displacements, flexibility displacements due to the damage. There are based on the Irwin J integral. And I use a simple eigenvalue. The method or the modeling is linear. Nevertheless, the topographical characteristic of the method make it a nonlinear approach, because the surface, the damaged surface from with the indexes are very complex, and you need to distinguish them. And the method allows for that distinguished selection of that. Now, this equation is very simple and provides a way to discriminate if you have damage or not. You can have as many modes as you can build from your experiment. If you have more better sensor capacity, then you will have more modes to watch and more possibilities of coming up with a better solution. These are two equations. In one of this is the same equation, and this is another one where you can use it only for circular cross sections. This is the flow diagram of the method. You start from here and then go over there to here. It would be too lengthy to explain it, but I'm going to try to do it graphically, so you would see it better. When I have integral case, you have this kind of modes: the first axial, the first bending, the same bending is the same. But when you begin to have some damage, 10%, 20% of the diameter, 30, 40, and 30, then the modes changes, and also the frequency changes in the flexural modes. Now, I build up these surfaces in order to show how the indexes form these three-dimensional surfaces. This is where the nonlinear part enters. The nonlinear part of the topography of the assumed locations. You have to assume numerically where the crack may be, but you have only one dimension, the actual dimension of the beam. So in this case, I'm thinking on 3% of the beam. In this case, it's 23% of the beam. Now, this axis is the depth of the crack, and this one is the mold numbers. What I did is to automate 50 calculations. Every 1% of the depth of the crack, there would be an index that you can compute for each mode. So if you interpolate, you come up with this surface or this surface, depending on where you assume the crack would be. Now, another refinement is you make a subtraction of a vector, and the aim that you should have is a straight line where one of them is, this direction is the depth of the crack, and these ones are the modes. So as we can see very quickly, this is not following a line, straight line. So this is not going to be a good choice. So, oh, sorry. So for instance, on the contrary, in this one, you have a very good prediction for 30%. In here, you have a prediction for 13%. 13% of the location of the beam is a lousy one, very bad one. But this one, 30%, you have a very nice straight beam. Oh, well, not straight, but close to straight, close to straight. Here is the experimental setup that I use. I use a free boundary condition with National Instruments data acquisition and a very bad accelerator. The accelerator had only 6,000 hertz, so it was not good. And I extended up to 20,000 hertz. So the more that you were going after 6,000, the worse the data was going to be. Now I know how to use a much better one to improve the method, to improve much more the method. So what I did also in the experiments, I put 4 different notches, of course, in different beams. I just put them in the same beam to show them, you know. I mean, this is in one port, another location, another location, another location. And I changed the material, I changed the geometry, I changed the dimensions, the diameter, and what else I changed? The depth of the crack, see, in order to make it more or less ample. And some recommendations are to hit in one direction with the impact hammer, but measure in the orthogonal direction. You will be able to get a better grasp of the breaking or the splitting of the crack. Here, for instance, I have integral beam in black color line, and in red color is case 2 with a deeper crack, which is 50% of the diameter and is located in the middle. The case 4 is 50% as well, but it is located in another part of the beam. And you can see right away the difference. This is experimental. This is experimental one. You can see how these indexes, damage indexes, are good. They will give you a good sense, a good method, because there are many indexes where you have to suffer to see, you know, what can you extract of them. In this figure over here, I have 5 frequency response functions belonging to the second and the third frequencies. It is not very well seen, but they split. They split, you know, and these are experimental ones. Now, for the criterion 2 regarding where the crack is, whether in one half of the beam or the other one, there are 2 possibilities. One is the method of anti-resonance shift, which has been abused from my point of view, claiming that it can locate, assess everything, damage existence, crack depth, location, and even its orientation. But I think this is expecting too much. Okay, and the other one that I have is based on the test that I do, and it can tell you very clearly where the crack is. These are the test results, you know, that I made some data. I put here until the 10th mode, but also I increase it up till the 16th mode. And this is the assumed location where you can see the, you know, the application of the method, and this synthesizing from P assumed. You have to assume how many locations you are going to use in your method. You have to do it more or less every 4 or 6% of the beam. And I have here the synthesis of them, comparing the, you know, there are 2 lines on each color, 2 lines on each color with 1 vector that I use from the test. You take a test and you obtain that one, you put it into the expressions, the splitting expressions, and then you come up with this final resume. for the 4 cases where you have error, a very small error in the word in the best point, and this is the worst. This axis is the length of the beam, so you're trying to obtain where is the location, and you make one refinement. With one refinement would be enough. So the conclusion is this is a practical and useful results obtained when detect damage from the very beginning, locate it, characterize it in one-dimensional structures. It is innovating with damage indexes, frequency split flexing indexes based. They're obtained from vibration measurements, which are very easy and practical to use, also in very high cycle fatigue, because very high cycle fatigue is actually based on vibrations. Finite element fracture mechanics are used for the development of the methods of the models, and the nonlinear approach results because of the topology of the surfaces. Experimental validation was coming all right, and this is the last one. It is simple and practical to perform vibration measurements. Vibrations are simple to obtain and cheap to obtain, to get. This can be applied to structural health monitoring or data-driven methods. And the main problem was my accelerometer, because it went up till 6,000 hertz. But I took data until 20,000 hertz. Not very good after 6,000. A wide frequency band and precise sensors would greatly enhance the performance, allowing a method to account for much larger number of modes, many more modes. Realizing precise slots, it was also another problem to do it in real practice, in real life. And you can use also some boundary applications as well. I'm ready to receive your comments and your questions, and ready to collaborate, proposal to collaborate. I have already achieved a couple of international collaborations between my institute and France. They're working right now, okay? And this is all, but I am ready for if there are any questions or comments.